Hey guys, Mr. Backward here. In this video, we're going to look at the definite integral. So in general, what we're going to be doing with a definite integral is we're going to be starting with a continuous function. So I'm going to call that function y equals f of x. And we're going to be looking at this function over a specified interval. And I'm just going to call that interval a to b as our general interval right now. Now, like we saw when we looked at that example where we had our parabola and we split that parabola into some different subintervals to help us create those rectangles to find the area underneath that curve, we want to divide this interval into some subintervals, and I'm going to call that delta x. That's the change in our x value going along the x-axis. So what we're going to do to find the distance, that delta x, we're going to take our end value minus our starting value and divide by the number of rectangles that we want to have. So this is kind of like finding the distance of that base value in our rectangle. Then what we need to do is find the height of our rectangle, and we did that by picking a point on the graph within our subinterval and plugging that value into our function. So let's say we were dealing with some general x sub 1 point. I would need to take that x sub 1 and plug it into my function to get the y value of f of x sub 1. Then once I know the height, this y value, that's the height of our rectangle, once I know that height, I can take that height times our base that we found earlier, and that's going to tell us the area of that individual rectangle. But then I would need to continue this process for an x2 value in our second interval, and an x3 value in our third interval, and so on and so forth. And then just like we saw in that parabola example, we're going to add up all of those individual rectangular areas. Now there's a fancy math way that we can write that. This E-looking symbol is a sigma, and that means that we're doing a sum. So what we're doing is we're taking our function and we're plugging in some general x values to get y values back. So this right here represents the height of our rectangle, but then we're multiplying that by the base of our rectangle, which we said we were going to call delta x. Now we're going to start with a value of 1, so we're going to do I equals 1 underneath this sigma, and we're going out to n number of intervals. This is what's called a Riemann sum. So this is basically a fancy math way of saying that we're finding all of these different rectangles underneath a curve, and we're finding the area of each one and then adding them all together. Now, if we do the limit of this Riemann sum as n is approaching infinity, then that's going to end up giving us the exact solution for the area underneath that curve, as opposed to just a general approximation of the area. And that limit, if it exists, is called a definite integral. So defining what a definite integral actually is. We're going to let our function f be a function that's defined on the interval from a to b, and we're going to let that Riemann sum be defined like we just talked about. The definite integral of our function over the interval from a to b, shown as this little squiggly line with our b value, the end of the interval, on top, and our a value, the start of the interval, on bottom, of our function f of x dx is defined as the limit of that Riemann sum as our n value is approaching infinity. And that's provided that the limit actually exists. And again, all of this fancy math notation means that we're finding the exact area underneath a curve, underneath a graph, over a specified interval. So in this example, we're going to look at computing an integral. So we're going to look at finding the definite integral on the interval from 1 to 5 of this function 2x dx. So what we've got happening in here is I'm going to draw out a quick picture of what this graph would look like. Looking at that function, it's y equals 2x, so that's going to be a line going through the origin with a slope of 2. And we're going to look at the interval from 1 to 5. So I'm going to say that 1 is this x value right here, and 5 is this x value right here. Now, as we're looking at finding the area, we want to figure out what this shape actually is. So if I go from this x-axis up to my line, and then if I go from this 5 on my x-axis up to my line, I'm I'm going to connect those two dots, and I'm going to connect them again along the x-axis. So we're looking at finding the area contained within this blue region here. Now this shape happens to be a trapezoid, and if we think back, the area formula for a trapezoid, we have to find the height of the trapezoid and multiply that by the sum of the two bases split in half. Now the height is perpendicular to the bases, so we've actually got some right angles happening in here. So this side going across the bottom right here actually represents the height of the trapezoid. So that distance in there going from 1 to 5, that distance is 4. Now the bases of our trapezoid are the two parallel sides. So this length right here is one of the bases, and this length right here is the other base. Now I need to take these end values of my interval and take them and plug them into my equation. That's going to represent those base lengths. So if I plug in that first end value, we would have 2 times 1 plus. Then I plug in my second end value, so that would be 2 times 5. But then I'm supposed to divide that by 2. Now 2 times 1 is 2. 2 times 5 is 10. So if we add those together on the top, we get 12. Divided by 2 is 6. So we've got 4 times 6, which happens to be 24. So this definite integral, the area underneath this graph on the interval from 1 to 5, that definite integral is 24. Now we're going to do another example, and it's going to be very similar to the last example that we just looked at, but the context is going to be a little different. So we're rolling a ball down a ramp so that its velocity after t seconds is always 2 times t feet per second. And we want to figure out how far the ball falls during the first 3 seconds. So we've got a velocity function. I'm going to call that v of t. And the velocity of our ball is 2 times t feet per second. So v of t is 2 times t. And we're looking at how far this ball is falling over the first 3 seconds. So as far as the interval goes, we're starting at 0, and then we're going to 3 seconds. So if I write out this definite integral, we'd have the interval from 0 to 3 of our 2t function. Now normally if our variable was an x, we would put a dx at the end, but because we're dealing with a t variable, I'm going to call it dt. Now remember, this definite integral means that we're finding the area underneath the graph on the specified interval. So if I do a quick sketch of the graph, it's going to look very similar to the last graph that I just drew out, starting at the origin with a slope of 2, so it's going to be a straight line, something like this. Now we're going from 0 to 3, so 0 right here, we're starting at the end of that graph, and we're going out to that x value of 3. So if I draw in this line here, we're looking at finding the area of this triangle in there. Now we know that area of a triangle is 1/2 times the base times the height. And the base and the height of a triangle always have to be perpendicular to each other, so I need to find these two lengths of this triangle. So if we're going from 0 to 3, then going across the bottom here, that distance should be 3. So we're going to take 1/2 times that base of 3. Now I need to figure out how tall this triangle is at that t value of 3. So I need to take that 3 and plug it into my function. So I'm going to be taking 2 times 3 to give me a height of 6. Now if I do 1/2 times 3 times 6, we should end up getting 9. Now this is a distance, and we're measuring this in feet, so this is going to be 9 feet. So during the first 3 seconds, that ball falls a distance of 9 feet. That's going to be it for this video. Thanks for watching.